In Module 3.6, we're going to be focused on embedded parameters. And the goal here is to explore different methods for solving for embedded parameters. We're going to develop the capacity to solve for any embedded parameter. We'll be using this technique in several different applications throughout the course of this book. And we're going to illustrate it here with a simple yield to maturity of a bond valuation bond valuation equation, and we'll look at some selected R code. Once we finish this presentation, we'll go look at the R code itself. There's numerous different ways of solving for an embedded parameter. You could just use a bracketed method of some sort and increment through the range. So you select some extremely low value, some extremely high value that has the answer in it, and then just increment through it and find the closest answer. One way to do this is known as the method of bisection. Basically, you find the midpoint. You consider the function of some upper and lower bound, and then so you consider f of a and f of m, and you compare it to f of m and f of b, where m equals half the distance between a and b. Select the region with the sign change and repeat. The secant method employs the slope at the initial guess to estimate the next evaluation point and repeat. In order to calculate this slope, that you'll have to use the actual analytic derivative or some numerical method. Newton-Raphson, you're going to need the first derivative function, which may be unstable and could cause some problems. The inverse quadratic interpolation method relies on 3 points to approximate. It's more efficient than a simple linear interpolation. Brent, which is often used in R, bracket the roots prior to starting the analysis, select numerical accuracy where the search will cease. It's basically a combination of bisection, secant, and inverse quadratic interpolation. For our purposes in modern technology, R provides several methods to find the implied parameter, and so it's really not that important to dive deep in this issue unless you run into some problems. So just to motivate why we need this kind of analysis, if you think about your typical bond value, remember in finance, particularly the discount factor adjusted approach, the value of some financial instrument is simply the present value of in this case, a bond, the present value of the coupons, present value of the par at some risk-adjusted discount rate. Well, if I have the market price of the bond and I have the coupons and I have the par and I have the maturity structure, I can solve for the implied yield to maturity. Basically, I can create a function where I have the bond value, I subtract off the actual price of the bond, and the goal is to find the yield that makes this equation equal to 0. And so if you think about the bond price yield relationship, it's convex. And so if I'm trying to find this point here, the idea is to find the yield to maturity that gives me the actual market price of the bond. And so there's a variety of different ways to approach this. One approach is you just build a bond value function. This is an illustration of this, and so you have some bond value, and the inputs are yield to maturity, coupon rate, par value, and years to maturity. And so I can compute basically the present value of these future cash flows in this function. I can then test the function to make sure it's working appropriately. With this FRM bond value function, I can then compute the difference. And so if I assume the bond value, the actual traded price is 90, I could calculate the difference, the price difference with the function by passing in the needed parameters, make a call within this function. Notice that we're calling the bond value function, and then we can just return the difference. And so we could test this, what this difference actually is. If the difference happens to be 0, then we have found the correct yield to maturity. An alternative way to do this same exercise is to, rather than call a function within a function, you can just build the calculations within this single function for the bond value. And you could do calculate the price difference that way. And the two methods should give you exactly the same results, whether you use a function within a function or you just use a single function to get the results. And so we could look at a variety of different maturities of bonds. If you'll notice, the slope of the price-yield relationship varies depending on the length to maturity. And so how you solve for yield to maturity is going to change. When we actually run this function, you can estimate how much error there was when the function ran, and letting yield to maturity go from 0 to 10. What we notice is when the yield to maturity is 0, the bond valuation is very simple. It's simply the sum of the coupons plus par. The search engine struggles a little bit there, but typically with any normal coupon bearing bond, it is extremely accurate, and even e to the minus 5 is very accurate. And so this particular method is working well. And so we basically introduced you to embedded parameters. It gives us the capacity to solve for any embedded parameter that we need. We illustrated this with yield to maturity and reviewed some code, and we will turn now to look at the actual code provided in the zip file related to Chapter 3 and this module. In Module 3.6, the provided source code is very simple. There's only one file, and so if I click on the project file, it will load the project background information. And this test program's already loaded, and so if we just begin going line by line to make sure we understand the basics, we assume a certain set of parameters as inputs. And if you'll notice, we have a lower bound and an upper bound, and we can compute the step size for graphics that are used later. As we illustrated in the PowerPoint presentation, one way to build out this function is you first come up with the valuation function. And if you'll notice, when you run this line of code, that function shows up down here. And eventually, when you have 25 or 30 different functions, you can jump between functions by just clicking on this. We can test to see if that gives us the right bond value. And so given these parameters, we have a $100 par, 5% coupon, yield to maturity is greater than 5%, which is yield to maturity is 6%. And so what we observe is that this bond is trading at a discount based on a 6% yield to maturity. If the actual price is $80, I know that my yield to maturity is not correct. It is not the equilibrium yield to maturity. And so to proceed, if we assume a bond value of, say, $90, and then run the difference function, what we observe is that there is a significant difference between the traded price of 90 and the bond valuation using a 6% coupon of 86. And so we need to use some sort of optimization routine. Another way to build this is the calculating the price difference with a function. That is, we embed the function in this existing function. Alternatively, we could just embed the calculations of the bond valuation within this function. Depending on your preference, we could run these calculations and they give us the same answer. So how do we find a yield to maturity? Well, we're going to use the optimize function, which is, if I go over here to the help, in case you're new to using optimize, and again, there's a whole bunch of different ways to do this. There's a description here of exactly how to use the optimize a function. And so this illustration, if you spend some time working through this, when you run this particular line of code, it produces a solution. The solution gives you both the answer, that is the yield to maturity that makes the actual price of the bond equal the model price, and it also gives you the amount of error in that price. And so I could print that solution out down here in the console, and so, or I could just move it over. I find it easier, rather than carrying around solution $minimum, let's import that into the bond yield to maturity and then do analysis in that way. The remainder of this code is simply doing a variety of different exercises. We'll compute bond values for a 1-year, 15-year, and 30-year bond. We'll estimate the yield to maturity based on those bond values, and then we'll look at the error of I start out with the yield to maturity. I estimate the yield to maturity using the optimizer, and then I'm going to look at the difference between my optimized answer and the actual yield to maturity. And so if you look at this code, basically I first start out with the yield to maturity. I give it a years to maturity. I calculate the bond value. Then I solve with this bond value. Notice it's here in the function. With this bond value, I'll calculate the yield to maturity. I'll store that in yield to maturity estimate for 1 year, and then I'll take a difference between my estimate and the actual to get the error. And so when I run this loop, it provides solutions to several different vectors. I could ask, what is the actual maximum error? In each case, it's identical, I found that a bit surprising. And when you look at the plot below, you'll see that it all stems from the zero coupon case. And so I could the remainder of this package just simply produces the price yield relationship. I find it easier to see if I make this a little bigger. And then I could plot the errors. And again, I recommend you spend a little bit of time with these plots just to get yourself familiar. Most likely you'll be using much more sophisticated plots that we'll talk about later in this material. And so this is basically the 30-year bond. This is the 15-year bond. In the 1-year bond, we can add a legend, which gives us lets us know which is which. And so basically our estimate of yield to maturity is very accurate. And so we now have the capacity to solve for embedded parameters and extremely complicated functions, some of which we'll do later on in this material.